Hello again, all. So, now that we know a little bit about decimals, we know what they are, we know how to compare them, and we know how to do operations with them, add, subtract, multiply, and divide. Well, now let's study what the forms of these decimals can be. So, kind of our end goal, I'm going to tell you what our end goal is. And this is what we're going to work towards. We're going to show that if a number can be represented as a fraction, then it can be represented as either a terminating or repeating, and I'll explain what these things are in a second, decimal. Not only are we going to show that, we're going to show the reverse as well. We're going to show that if a number can be written as a terminating or repeating decimal, then it can also be written as a fraction. So we get this biconditional, which we talked about a little bit at the start of the term. So if a number can be represented as a fraction, then it can be represented as a terminating or repeating decimal. And if a number can be represented as a terminating or repeating decimal, then it can be represented as a fraction. So that's our goal. So let's talk about some fractions first. So if I wanted to represent a quarter as a fraction, well, I think we all know how to do that. That is 0.25. Long division will get you there too. No problem. It's a nice terminating decimal. It doesn't repeat forever. It just stops. But we know how to write decimals as fractions. We know decimal fractions. So this is 25 hundredths. No problem there. And you can see, well, 1/4 is equivalent to 25 hundredths. We can just multiply top and bottom by 25, and we get 25 hundredths. And the other thing I wanted to show you guys, well, let me write it like this. We'll see why this is important later. But I can write this, if you like, as, well, 100's 10 squared, or 10 times 10, which I'm going to write in its prime factorization. So this is 25 over 2 times 5 times 2 times 5. So I have 2 2's and 2 5's multiplied together. Everybody happy with that? And if you look at a quarter, well, a quarter is just 1 over 2 squared. So we can see it's equivalent if I multiply by kind of the missing 5's here, so that we get a power of 10 in our denominator, then it's a decimal fraction. Then it's 25 over 10 squared, or 25 over 100. And that's kind of the idea throughout. So anytime we can make the denominator a power of 10, then we can write it as a decimal fraction. So if a fraction is equivalent to a decimal fraction, A over B can be represented as a terminating decimal. So that's kind of our idea here. Any time that we have this equivalence to a decimal fraction, we should be able to write it as a terminating decimal. Let's look at another one. So, is 121 over, let's say, what? Let's say 1,250. Is this a terminating decimal? Or maybe can this be? Can that be represented as a terminating decimal? Well, let's look at our denominator. Remember, whatever is in the numerator, in some sense, doesn't matter. We'll talk about that in an example after this. But let's look at the prime factorization of 1,250. So I easily see a factor of 10. So 10 times 125 is 1,250. 10 is, of course, 2 times 5. They're both prime. And 125 is 5 times 25. 25 is 5 times 5. All of those are prime. So I can write 1250 as 2 times 5 to the, well, I have 1, 2, 3, 4 5s, so it's 5 to the power of 4. So I know 121 over 1250 equals 121 over, well, 1250 is the same thing as 2 times 5 to the 4. And remember, if this is equivalent to a decimal fraction, we're good to go. So all we have to do is see if we can make it equivalent to a decimal fraction. So remember, 10 is 2 times 5. So we already have one 10 in here. Here it is here, 1, 2, and 1, 5. We have 3 other 5s that don't have a matching 2. But we can multiply top and bottom. Oh, that's not what I want. We can multiply top and bottom by some matching 2s. So we have the same number of 2s and the same number of 5s in our denominator. So now this is, well, whatever 121 times 8 is, we'll figure that out in a second, over, well, now it's 2 to the 4 times 5 to the 4, which I'll simplify. Well, 121 times 8, let's do that little calculation here, 968. So that's 968 over, using our rules for exponents, well, we have 4 copies of 2 times 5. This is 2 times 2 times 2 times 2 times 5 times 5 times 5 times 5. Let's use commutativity and associativity to group it up as 2 times 5 times 2 times 5 times 2 times 5 times 2 times 5. So what is this? This is 968 over, well, 10,000, a 1 with 4 zeros after it. And what is this as a decimal? Well, as a decimal, well, we have our, so it's going to be 0. Well, we have our tenths, hundredths, thousandths, 10,000ths place. So we have 968 10,000ths, so we put a 0 here. So this is 121 over 1250, written as a decimal. And you can check that with your calculator if you like. So let's move on and do another example. What about 7 over 15? Is this equivalent to a decimal fraction, and therefore able to be represented as a terminating decimal. Well, let's look at it. This one's small, so it's kind of easy to see what's going on. So 7/15. Well, 15, I don't need to do a factor tree. That's 3 times 5. So is this equivalent to a decimal fraction? Well, can I multiply by my denominator by anything to make it a power of 10? Well, here I can't. So I can't multiply my denominator by anything to have it equivalent to a power of 10. And the problem is, remember, 10 is 2 times 5. So any power of 10s has to have just 2's and 5's in it. But we have this 3 here. So whatever I multiply by, since I'm multiplying the top and bottom by that 3 is not going away. So anytime I have a prime that isn't 2 or 5, for the most part, there's one caveat, then it's not going to be able to be represented as a terminating decimal. So since the denominator of fraction, and let me put an asterisk here because there's a caveat that we need to talk about in a second in the next example. So since the denominator of the fraction has a prime factor besides 2 or 5, we cannot write 7/15 as a terminating decimal. Okay, so let me do an example to kind of explain why we need to be just a bit careful. So what about, oh, I don't know. Let's do 21/120. Okay, again, let's factor 120. That's 12 times 10. 10 is 5 times 2, looking good so far. But 12 is 4 times 3. So 120 is 2 to the 3. Here's our 1, 2, 3 2's. We have 1, 3, and 1, 5. So you could think, oh, we have a 3. But let me just write this down for a second. So 21/120 equals 21/2 cubed times 3 times 5. Now here's the thing. That 3, you could think, well, that stays around. It can't be written as a decimal fraction. But note that 21 is 3 times 7. So we have 3 times 7/2 cubed times 3 times 5. So we can make an equivalent fraction. We can reduce it to lowest terms where that 3 cancels out. So this is the same as 7/2 cubed times 5. So, can this be written as a decimal fraction? It absolutely can. The only primes we have in our denominator when the fraction is in lowest terms are 2 and 5. We like that. So we can just say, yes, it can be expressed as a decimal fraction. And it doesn't say what one it is, but we can figure that out. So we have 3 2s and 1 5. In order to make powers of 10, we need the same number of 2s and 5s, so we need 2 more 5s. So we get that 7 over 2 cubed times 5 is equivalent to, well, 7 times 25, you can check, is 175. 7 quarters is $1.75. Over, well, we have 3 2s and 3 5s, so we have 3 tenths. So we have, that's not the color I want, so we have 1,000. So 21 over 120 is the same as 0.175, 175 thousandths. So this asterisk down here, this asterisk up here, I'm going to explain down here is what I mean. That asterisk means when the fraction is in lowest terms. So when you've simplified it completely. Once you've simplified it, then ask, does my fraction have any prime factor that isn't 2 or 5? After you cancel out everything you can, then you can ask. All right. The final thing that we'll talk about is fractions that are not equivalent to terminating decimals or decimal fractions. So what about that case? So let's look at one that we know. Let's look at 1/3. I think you could do long division. In fact, maybe let's do the long division. So 3 into 1. Well, let's get a couple of decimal places here so we can see what's going on. 3 goes into 1 0 times. 3 goes into 10 tenths 3 times. We'll have a decimal place lined up. Subtract 9. We get 1. Bring down your 0. 3 goes into 10 hundredths. Well, this looks pretty familiar. 3 times. Subtract 9. Left with 1. 3 goes into 10 thousandths 3 times. Subtract 9, you get 1. And that keeps going forever. You can see this pattern repeat. So we can write this as 0.3 repeating. And just a couple of nomenclature things. So the thing under the what do I want to say? Sorry. The decimal bit that repeats, this is called the repetend. So the repetend for this is 3. And so let me just give you another example. So 0.27 repeating. Here is our repetend. It's 27. And that is 0.27272727 off forever. So our repetend in this case is 27. And the next thing is the period. So the period is just the number of digits in the repetend. So in this case, in the first case, the period is 1. There's only one digit that repeats. So the period in this case is 1. And 0.27 repeating, the period is 2. Now a couple of notes about repetend before we talk a little more. So with repetends, they must be the first and shortest repeating pattern. So you want to minimize the period and you want to make it come as early as possible. So what do I mean by that? Let me give you a few examples with that 0.27. So if it was 0.27272727 all the way infinitely far to the right, well, if we wrote it as 0.27 like that, that's good. That's the smallest thing that repeats, and it comes first. So if I wrote it like 0.2727 repeating like that, well, I could write it shorter. I could just write 0.27. So this is no good. So we want the first and shortest repetend we can get. So that's no good, and neither is this 0.272727. We could have had a repetend start earlier, so that's no good either. So that is the period and the repetend, just to talk about a nice way of writing repeating decimals. Okay, so I want to convince you that any fraction that isn't a terminating decimal is a repeating decimal. So let me try and convince you of that. That cannot, any decimal that cannot be written as a terminating decimal can be written as a repeating decimal. So I'm going to do an example here. And rather than a proof, I'm just going to do a proof by example, which usually isn't good, but the details are a little tricky to write down. So by example, so usually this is bad, but for our purposes, I think it's okay. So I'm going to put a little like one of these faces there, so that to remind you that this isn't the best thing to do. It's not a real proof, but it does get the point across. So let's do something along the lines of let's do 2/7. Why not? Just something a little different. Let's do 2/7. So I'm dividing by 7. So the possible remainders are 0, 1, 2, 3, 4, 5, and 6. So I'm going to do some long division. It's the wrong way around. I need to have the divisor on that side. So 7 into 2. Let's put some decimal places in here just to see what happens. All right, 7 goes into 2 0 times. 7 goes into 20 twice. So 7 times 2 is 14. We subtract 14 tenths. We're left with a remainder of 6. So we're left with a remainder of 6, and we're pulling down this 0. So you can think, any time we pull down a 6, or we get a remainder of 6 and pull down a 0, we've already seen that, so we know what's going to happen. So anytime we run across a remainder of 6, we know what's going to happen. So I'm going to cross that out because we've seen that. The other thing, if we ever run across a remainder of 0, well, that means we just stop, so it terminates. But we know 2 over 7 isn't going to be a terminating decimal. Since 7's a prime number, it's not equivalent to a decimal fraction. I'm going to cross that out as well. So the remainders we can possibly see again before it starts to repeat, if it does start to repeat, are 1, 2, 3, 4, and 5. So let's keep going. 7 goes into 68 times. 8 times 7 is 56. We subtract. We get a remainder of 4. So anytime we see a 4, we know what's going to happen. So we'll bring down our 0. 7 goes into 45 times. 5 times 7 is 35. Subtract. We get 5. So anytime we see a 5 now, we know what's going to happen. We bring down our 0. 7 goes into 57 times. 7 times 7 is 49. Subtract, we get 1. So anytime we see a remainder of 1, we know what's going to happen. So we're running out of remainders here quite quickly. So 7 goes into 10 once. 1 times 7 is 7. Subtract, we get 3. So we see a remainder of 3. So anytime we see a 3, we know what's going to happen. We bring down our next 0. 7 goes into 30 4 times. 4 times 7 is 28. We get a remainder of 2. And now we're out of remainders. So anytime we do a subtraction, we're going to get a remainder that we've previously seen. So this time, well, we're going to get 7 times 2 is 14. Hey, look at this. We've seen this before. Get a remainder of 6. And we know what happens when we get a remainder of 6. We know we're going to get a remainder of 4 next time, and then a remainder of 5, and then a remainder of 1, and then a remainder of 3, and then a remainder of 2. And then it'll just keep repeating that pattern. So once we see a remainder we've seen before, when we start bringing down the zeros, because anytime we start bringing down those zeros, well, once we keep bringing down zeros, we kind of know what's going to happen when we find a repeat remainder. So I can write 2 over 7 as 0.285714, and then it's going to start repeating. And you could think, well, there's nothing special about 2 or 7. Whatever we divide by, whatever our denominator is, well, it's going to have 1 fewer possible remainders. And eventually, we're going to run out. So that's the idea. Let's write that up. So, in general, if A over B cannot be written as a terminating decimal, when we long divide A divided by B and start bringing down zeros, we will eventually run out of new remainders. Since there are only, well, if you're dividing by b, there's going to be one less non-zero remainders. Remember, it definitely can't be 0, because if we ever get a remainder of 0, we're done doing long division, so the decimal will terminate. So we'll eventually run out of new remainders. When we see a repeat, we know the decimal. Expansion will repeat. Now, 7's kind of a special number in some sense, in that you definitely see every remainder possible when you divide by 7. So you see a remainder of 1, 2, 3, 4, 5, and 6. But that doesn't always happen. If we look at something like 3 over 11, where there's 10 possible remainders, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but 0 isn't one of them, because if we get 0, we know the decimal terminates, and we know this is a non-terminating decimal. So when we do the long division, let's see what happens. So we get 11 goes into 30 twice. Remainder of 8, bring down our next 0. 11 goes into 80 7 times. 7 times 11 is 77. Get a remainder of 3. Bring down our 0, but we've already done this. That's right here. So once we introduce those those zeros to the right, anytime we see a repeat, we know what happens. So we've only seen the remainders 8 and 3, but the next remainder we get is 8. So the remainders in this case are going to keep alternating